I was about a minute off, so we'll just go ahead and start right now. Just remember, there is no lecture on Monday, and there's no lab on Tuesday next week. So as far as this class is concerned, your entire week is free. On this week's retrospective on Piazza, we'll go ahead and announce how the rest of the semester is going to go with those 2 weeks after the break. In particular, we're going to shift a few of the due dates ahead by a couple of days, not too dramatic. But then we also have details on your resubmission opportunity for one hack and one lab during that final 2 weeks. Okay, so details of that will be in this week's retrospective. What we're going to be doing for the rest of the day here is answering the question of that we posed last time: can we do better than that linear search algorithm that we developed? So just to remind ourselves of what it looks like. Again, the basic idea is that given a collection of elements, you simply start at the beginning and you sift through your haystack looking for that needle. The first key element that matches your key element, that's the one that you end up returning. How efficient or complex is linear search? Again, you have to look at it from the worst case scenario. You can look at it from the best case scenario or the average case scenario. In either case, the worst case scenario or the average case scenario here is going to end up with a linear function, thus the name, linear search. The perspective here is that suppose that you were trying to search an array of 1 trillion elements. And by today's standard, that is not big data at all, right? That's only about a terabyte of information. Your typical hard drives will hold more data than that, right? My hard drive on this computer right here is 2 terabytes, I think. A typical desktop computer is going to have way more, right? Built-in hard drives now are going to be magnetic drives even are still, what, 10 terabytes or so, right? Maybe more. And so this is not at all big, right? But it would make about 1 trillion comparisons in the worst case, 500 billion in the average case, right? Consider the growth rate there, that if you went from 10 trillion to 100 trillion, you would be doing 10 times as much work for linear search, okay? Anytime that you try to increase by an order of magnitude, going from n to 10n, right? 1 million to 10 million or 10 million to 100 million, you're going to see a noticeable decrease in the time that it takes to execute that operation by an order of magnitude like 10 times slower, right? The same order of magnitude. So now can we do better? As we previewed, I thought we previewed, that you're playing this game on The Price is Right, and you're guessing, right? From the prices from 1 to 100. Or on your, I think, Lab 5, you did the guessing game, right? Where I'm thinking of a number between 1 and 100. What is the optimal strategy? To simply choose the middle element, 50. And then you have more information on, well, it's lower or it's higher. You have cut the input from 100 down to only 50 possibilities, right? You do the same thing over and over again. You go from 50 to 25, 25 to 12 or 13, 13 down to 6 or 7, right? Then you're narrowing in on the actual price, right? And you're only asking one question at a time to cut it in half. What kind of a speed up is that, and what kind of an algorithm is that? So to understand that, let's go ahead and pull in. I need to go to the proper class here. There we go. Let's pull in this array right here. All right. We're going to search this array. Oops. Search for 42. Right? We're searching for this guy right here. Now, if we were to use linear search, we would start at the beginning. That's not it, that's not it, that's not it, all the way over here until we found what we were looking for, right? But what can you tell me about this array? Take a look at it real close. What can you say about the elements? They are in order. They are sorted, right? How can we exploit that idea the same way that we exploited the 1 to 100 idea, right? The guessing game idea. Well, as hinted by the highlight here, don't look at the left and right. Don't start at one end and go all the way to the right. Instead, start somewhere in the middle, right? Somewhere in the middle, exactly in the middle. So what I'm going to do is I'm going to show you how this kind of search will work by keeping track of a couple of things. For example, we're going to keep track of a left index that I'm going to start at 0. And we're also going to keep track of a right index that I'm going to start at 10. Why? Because that's how big the array is. I'm going to start my left index here and my right index right here. And what I'm going to do is I'm going to move them in until I've found what I'm looking for or something else happens that you're already familiar with from Tuesday. All right, so the idea here is I'm going to look in the middle. Just like the guessing game, I'll guess $50. In this case, I need to compute this index right here. If I've got a left index of 0 and a right index of 10, how do I get an index of 5? A middle index. How do I compute that generally? Okay, so right minus left divided by 2. Right? That'll work on the first iteration here. But in general, what if it was 2 and 6? What's the middle index then? 4. So 6 minus 4 is 2 divided by, 6 minus 4 is, 6 minus 2 is 4 divided by 2 is 2, but that's not the middle index. So what do you need to do if you're going to do that? You start at the left and then you do that stuff. And that's exactly what you should do when you program it. But we're going to go ahead and call that something else because this is pseudocode to start out with, right? So that's called the, if I've got a number here and a number here, what's the number right in the middle of them? Midpoint. It's also called the average, right? Left plus right divided by 2. Right? In this case, that's going to be what? 10 plus 0 divided by 2 is 5. That gives me this thing right here. Okay? Now I've got some decisions to make. Well, first of all, is that the thing that I'm looking for? Nope. So the value a sub m in my array is not equal. Is it equal to the key? If so, done. Right? You found it. Otherwise, in this case, it's not. What am I going to end up? I'm searching for this key right here. What's its relationship to 12? 42 is greater than 12, right? So if the key is greater than the thing that I'm looking for, then I need to search right. Right? Search in the right part. This part right here. Now to do that, what am I going to have to do with my indices? My left index is right here, and my right index is right here. So I need to update my left index to be 6 in this case. All right? So I will update my left index to be 6, and now I'm looking at just this subarray right here. I've effectively cut out half or more than half of the array already. And why am I able to do that? Because it's sorted. Right? If 42 is greater than this element and it's sorted, then I know that it lies in this half of the list, or this half of the array. Right? So continue. What's my new middle index? 10 plus 6. What's the average there? 8. So here's my middle index now. All right, oops. And I'll highlight this. Here's the next one. There we go. 102. Is that the thing that I'm looking for? Nope. Not done. Right? But 42, is it great? If the thing I'm looking for, is it greater than 102? 42, is that greater than 102? Nope. So if the thing I'm searching for is less than what the middle thing is, where do I go? I search left. In this case, I update. Let me go ahead and, can I highlight this? And move, nope, undo. Okay. Search left. I'm just going to have to erase it. And I end up looking at this part of the array. Meaning that I update my right index to what? It was 10 before, now it is 7. Whatever the middle index was, minus 1. Okay? Repeat. What's my new average? 7. 6 plus 7 divided by 2 is equal to 6.5. Is that an index you've ever heard of? Nope. So what are we going to have to do with that index? Truncate. Exactly. And my new middle index here is now 6. Okay? Once again, I highlight this. Is 34 the thing that I'm looking for? Nope. Is 34 greater than, or is 42 greater than 34? Yep. So what do? I search right. And I end up updating this to just that one right there. Now, what's the average of 7 and 7? 7, right? So I've found what I'm looking for, and I'm done. What if I were not searching for 42? What if I were searching for 41 instead? What would happen on the next iteration here? What if I were searching for 41? Well, 41 is greater than or less than 42? Less than. So what do I end up doing with my range here? It ends up looking like that. The left index and the right index have gone past each other. Right? What did you do in that situation when you were computing whether or not something was a palindrome? You stopped and you said, what? Yes, it is a palindrome. What do I do in this situation? I'm searching for 41. Does 41 exist in that array? Nope. So if left and right pass each other, what do? I say, does not exist. Unsuccessful search. Okay? Let's write this out. This is known as binary search. It's known as binary search simply because it's cutting the input in half each time in 2 parts, binary 2, right? Binary search, and we're going to take an array, a key, a left index, and a right index. The reason that we're going to take all those things is because what's the nature of the algorithm that I was describing here? You look at a range and you didn't find what you were looking for, so you look at a different range. You didn't find what you were looking for, so you look at a different range, until you get to what you need to be looking at. That sounds recursive to me. So let's write a recursive version of this. Here's my input. It's exactly almost the same as a collection, as linear search, in that you have a collection, A, of elements A1 through AN. Right? You have a key, K, and a left and a right index, or indices, L and R. Right? I'm just writing them as L and R so that I don't have to write out left and right every single time. Right? My output is going to be on element A in A, such that A is equal to the key. Okay? Otherwise, phi if no such element. Okay? If this is going to be a recursive function, what's the first thing I need to think about? When you wrote your recursive functions, what's the first thing that you did, other than error handling? Base case. So what's the base case here? Left and right index have gone past each other. If the left index is greater than the right index, we stop and output phi, because we didn't find what we were looking for. Right? Otherwise, we go through these series of questions. Is this the thing that I'm looking for? Or is the thing I'm looking for in the right half or in the left half? In which case I do one recursive call or another recursive call. So I need that middle index here. That's simply going to be left plus right over 2. Right? And this is the middle index. Ooh, that's interesting. I wrote a left arrow here instead of the equals operator. Why? The assignment operator in C, right, is almost universal, but not all programming languages do that. Maple and maybe I think COBOL, or maybe it's Fortran, I forget, has an assignment operator that's a colon and an equals. I think somebody here said that they had some Haskell experience. What's the assignment operator for Haskell? Does anybody remember? No? Less than, and then a hyphen. What does that look like? Arrow. take this expression and put it into this, this variable. Right? Pseudocode, that's why I'm doing it. Okay? If the thing in the middle is equal to my key, output that thing. And you're done. Otherwise, if that's not what you're looking for, then you need to look at the right half or the left half by updating your left index or your right index appropriately. So, if the thing that I'm looking for, k, is less than the middle element, then I will recurse left. Right. So what is that going to look like? Well, it's going to be a call to binary search. The array doesn't change. The key doesn't change. If I'm going to recurse left, what do I do? Get rid of all this. So if I'm going to end up on the first iteration here, if I'm going to recurse left, do I change the left index? Nope. This is my middle index right here. So what do I do with my right index? Make it equal to m minus 1. So left index and m minus 1. Else if the thing I'm looking for is greater than the middle index, then I will recurse right. And that's going to be a call to binary search on an unchanged array, unchanged key, and the left index gets updated to, oops, sorry. There we go. The left index gets updated to m plus 1. The right index stays the same. Why minus 1 and plus 1? Do we need to look at the middle element again? No. We already said that that's not what we're looking for. There's a recursive version of binary search. Okay? We're going to go ahead and program this in C in a moment, but we're not going to do it recursively because recursion is costly. Right? Now, we're not going to be able to be doing extra work, right? Where it's not like memoization is going to save us, but it's just that the overhead is not worth it. I can take this and I can translate it to a simple while loop. Right? Left and right index, while they haven't passed each other, just look at the middle element. And I'm running out of hands here, right? Just look at the middle element, right? And then change your index appropriately, right? Until they pass each other. That sounds like a while loop to me, rather than just recursion. Before we do that, though, let's go ahead and analyze this. Now, it goes a little bit beyond the scope of this course to formally analyze this. Instead, what I'm going to do is I'm going to make some observations. So here's the size of the array. To start out with, we have n elements. All right? Now, I'm going to look at this from the worst case scenario because that's how we looked at linear search. And what I'm going to do is I'm going to keep track of the number of comparisons required to do this. So number of comparisons, comps. The first comparison that we did cut it essentially in half, n divided by 2. We only did one comparison. Now let's go back to the pseudocode here and see where that comparison is. Is this the comparison that we're talking about? No, that's just our base case. That just tells us when we need to stop the program. Just like when we analyzed linear search with respect to its for loop, we ignored everything in the for loop, like the control structure of the for loop. We focused on what was going on inside that loop. I'm going to focus on what's going on inside the actual algorithm rather than just the base case. I'm making a comparison here, here, and here. Now, strictly speaking, is this comparison right here necessary? No, it's either equal, less than, or greater than, right? I wrote it with an else if statement and a condition here, but I didn't need to do that. Just go ahead and get rid of all this. There we go. And now I'm down to 2 comparisons. But are they really different comparisons? Not really. Even if you wanted to treat them as 2 different comparisons, right? Ultimately, whatever the number of comparisons is, some function here, then there's going to be a 2 out front. Who cares about that 2? You take your program and you move it to hardware that's twice as fast, and guess what happens? There's a 1/2 out front because it's twice as fast. You take your program and move it to old hardware that is twice as slow, and what happens? There's another 2 out front. So who cares about that 2 out front, those constants out front? We're not going to get into big O notation in this course, but that's what I'm hinting at. Right? I don't care that these are 2. And then my second justification for treating these the same is that in practice, we're not actually going to be making these comparisons. We're going to be calling a function. Here are 2 things: students, airports, numbers, integers, characters. It doesn't matter. I don't know how to compare them, so I'm going to hand them off to something called a comparator that returns something negative, 0, or something positive depending on the relative ordering of those things. Does that sound familiar? Something's negative, 0, or something positive depending on, does A come first and B second, or B comes first and A second, or they're equal. Where have we seen that pattern before? String comparisons, strcmp. Right? So when you count the number of calls to strcmp, you just treat that as one thing, right? Checking whether or not the result is 0, negative, or positive, that's part of the control structure of the algorithm. Right? So I'm only making one comparison to cut it in half. On the next iteration, how many comparisons do I make? 1 to cut it in half again. N divided by 2 divided by 2. Simplify that for me, math folks. N divided by 2 divided by 2 is going to be? N over 4. Right? Next iteration, we do one more comparison to cut it in half again. 1/4 n cut in half is going to be? Follow the pattern. N divided by 8. One comparison, dot, 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 dot. Right. What's the pattern here? In the denominator? 1, 2, 4, 8, 16, 32, dot, dot, dot. Ultimately, what is this going to be? N divided by some power of 2. And I'll just call it k. You make one comparison there to cut it in half again, dot, dot, dot. When do you stop? So left, right, left, right, left, right, left, right. And they're past each other. You don't make a comparison here. The last comparison that you made was when they're equal, when the size of the array was 1. Right? So how many 1s do I have here? 1 plus 1 plus 1 plus 1. How many times? Number of 1s is equal to the total number of comparisons. Well, the number of 1s that I have is equal to n divided by 2 to the k. When that hits 1, that's how many lines I have. I have 1 line, 2 lines, right? You can see that, right? There's a 1 to the 0 here, 1 to the 1. This is 2 squared. This is 2 cubed, right? And then this is finally 2 to the k. So all I have to do here is solve for k. Again, math folks, help me out. The easy part is to take 2 to the k onto the other side, right? N is equal to 2 to the k. The hard part is getting k alone. So how do I solve for k? What? Log. Okay, what kind of log? Log base 2 of n. Log base 2 to the k. Right? What happens to that k? Comes out front. Right? Log base 2 of 2. What happens to log base 2 of 2? It goes away. Right? It's 1. So in other words, k is, or binary search makes at most k equals log base 2 of n comparisons on an array that originally had n elements in it. Okay? Let's put that into perspective here. Log base 2 of that 1 trillion that I was talking about. How big is 1 trillion? 10 to the 12. 10 to the 12. Right. This is 1 trillion elements. What's that equal to? No idea. Well, what could I do that 12? Take it out front, right? And then log base 2 of 10. How big is that? 3 point something something something. All right. I don't know what it is either. If you want an exact amount, let's go to Wolfram Alpha. Right? So log base 2 of 10 to the 12. 39.89 dot dot dot. We'll just say that it's 40. 40 comparisons instead of 1 trillion, right? Versus 1 trillion comparisons for linear search. This is binary search. Is that a difference? That's a huge difference, right? Only 40 comparisons is a blink of an eye. 1 trillion comparisons, that's probably a couple minutes of computation time on a crappy computer, right? So, what is the relationship between these two, right? What if going from log n, log base 2 of n, to n, right? Again, this is binary search, and this is linear. What would I need to do to this function right here to get n? Exactly what I did over here, but in reverse. In other words, 2 to the log base 2 of n is equal to n. In other words, the interpretation here is that binary search is exponentially faster. It's a huge difference. Okay? Another way of looking at it, right? If I went from n to 10n with linear search, right? It took time t before. Now how long does it take? 10t for linear search. If I did the same thought experiment here, and I went to 10n for binary search, which is log n, right? T is equal to log n. What happens now? T becomes log base 2 of 2n. Right? So again, math folks, help me out. What is log base 2 of, oops, sorry, 2? I meant 10. Come on. 10n. Right? 10n. There we go. So, log identities. Log of AB is equal to what? No? We're bad on our log identities? A times B is equal to log of A plus log of B. Right? There we go. So this is going to be log of n plus log base 2 of 10. Right? And once again, Wolfram Alpha will help us out with that. I'll just take out the exponent here. And it's something like 3.3. So in other words, fewer than 4 additional comparisons. Remember, with linear search, we went up by an order of magnitude. Right? So if we were doing 1 billion comparisons before, now we're doing 10 billion comparisons. But by going up by an order of magnitude here with binary search, we only do 4 more. Not 1 billion more, not 1 trillion more, just 4, right? Or 1 or 2. You can count on one hand the number of additional comparisons that you'd end up doing. Right? All right, the last way to look at this would be from the calc perspective. So put on your calc hat for a second and remind me, what's the growth rate of a linear function? The first derivative, which is 1 here. Ooh, now here's a good question. What's the derivative of log n? Log base 2 of n. What's the derivative of natural log of n? Good. 1 over x. Over here, it's the same thing. You just need to put on your algebra hat or whatever, and realize that you can always change the base, right? So this will end up being 1 over natural log of 2, who cares, times 1 over n, right? So I'm just going to ignore this as some constant c, okay? It's still 1 over x, 1 over n. In other words, what about the growth rate? Is it growing? Is it staying the same? No. What's happening as n tends towards infinity? It's getting closer and closer together. In other words, it's slowing down, right? Certainly, you'd be able to at least graph it, right? Here's, come on, there we go, snap 2. There's our linear function, n. What does log n look like? Something like this, right? Okay, it's not a parabola, but it'll keep on growing, but it'll go going up. But the rate of growth at which it's growing is slowing down, right? It's decelerating. There's no comparison here between these two at all, right? Binary search wins hands down. What's the problem? What do we need? Needs to be sorted. Right. So let's come over here and implement it while that's restarting, right? Come on. Any questions on binary search while we're waiting for it? No? Well, then while we're waiting for it, I'll show you some practical applications here, right? No, I want my CS1 book. There we go. I grabbed this many years ago when Windows 7 was still a thing. Where is it? Well, now it's up, but this is still a novelty. It's nice to look at. Binary search. There we go. Why do we use binary search? I mean, it goes beyond just, computers, right? I asked this of the morning class, but does everybody here should know what an index card is, right? This little tiny 3x5 index cards. Why do we call them index cards? Where are they used? In a card catalog, right? You want to look up something pertaining to some historic event, like the Kennedy assassination or something like that. What do? Well, you go up to the librarian and say, give me a book by this, right? And then they do all the work? No. What are they going to end up doing? They're going to go to the card catalog. And are they going to start at the beginning of the card catalog and go A's, B's, C's, D's? No, what are they going to do? They're going to jump to K's. And when they're there, they're going to jump to the KEs. And then they're going to jump to the KEDs for Kennedy, or KENs for the Kennedy assassination, right? That's what indexing is. You go through all of these subjects and you sort them so that you can exploit that sortedness, right? Here it is in practice on your own computers, right? It's still used today, right? I tried searching for something on my old Windows 7 machine many years ago, right? Searches might be slow in non-indexed locations. What does that mean? If it's non-indexed, it's not sorted. If it's not sorted, what do you got to do? Start at the beginning and look at everything. If it's indexed, if it's sorted, what can you do? You can exploit binary search and only look for certain things, right? If it's sorted. This happens, even today's computers are like that, right? In the background, they're indexing stuff. Google, in the background, it's web crawling and indexing stuff and updating its index so that your search is instantaneous rather than taking forever. Because imagine if to search for, I don't know, the FIFA results that start this weekend, right? what's the score of this such and such game, right? And if it had to look through everything that was completely irrelevant, oh, okay, well, the Chiefs score is this, and the Blackhawks score is this, right? Just completely irrelevant sports, right? It would take forever, right? That's why we like sorted things. We like structure because we can exploit that structure. Now, with the remainder of our time, since it's now come up, let's go ahead and implement this. I'm going to go ahead and get rid of all of that old stuff there and change this back to int. And we'll go ahead and search, say, for one, let's say 3. Let's search for 6. There we go. The first thing. I'll go ahead and keep index of here. Index of. I'm going to go ahead and get rid of this version, though. And I'm going to go ahead and reprogram this as a binary search algorithm. Int binary search. All right. Okay. We're going to take an array, its size, and the key. But I'm not going to take the left and right index because I'm not going to do it recursively. I'm going to do this iteratively using a while loop. While this finger and this finger have not yet met, keep going. Is the thing in the middle you're looking for? No. Okay, well then recurse on this part, or reiterate on this part, reiterate on that part. So to start out, I'm going to have to set up those indices. Int left is equal to something. Int right is equal to something. Where do I start my left index? At the beginning of the array, which is index what? 0. My right index is going to start at the end of the array, which is n? Yeah, the size minus 1. Thank you. I was using n versus size, right? Size minus 1. I'm not going to have a for loop. Instead, I'm going to have a while loop. While the left index and the right index have not passed each other. In other words, while the left is less than or equal to the right, look at the middle index. Int middle is equal to left plus right divided by 2. Is that correct math? Nope, that's not the average. That's correct math. But unfortunately, if you're actually going to program it like this, you are risking overflow here. What if you had a very, very large array of 2 billion elements, right? 2 billion, and then your left and right index are zeroing in over here in the right part of the array. So it's about 2 billion and 2 billion. Can you add those together and store that in an integer? Nope. 4 billion would end up in an overflow and give you a negative index value. Is a negative index value going to work for you? Nope, that's going to be a segmentation fault. Right? So in practice, don't do this. Right? What's a better way of doing it? The one that you described, left plus right minus left divided by 2. There's no overflow there at all. Right? This is mathematically correct, but engineering-wise, it is bad because we know we're computer scientists and we know about the limitations of finite representations. Unfortunately, even the best computer scientists can make that mistake. A bug similar to this had existed in Java for over a decade, right? And it was never really reported because it only manifests itself when you've got huge arrays, like arrays of several billion elements, or up to a billion elements, which rarely ever happened. It was only fixed like 10 years later. It had existed. Nobody had ever reported it. Nobody had ever fixed it until finally somebody recognized, you've got overflow here because I actually had a huge array. And wow, you're the first person in 10 years to have a huge array. Congratulations, right? It never came up. Or they just said, oh, okay, it must be somebody else's bug. I don't know. Right? So let's go ahead and correct this. Left plus right minus left divided by 2. There, no overflow there at all. That's the exact same math. Right? All you have to do is say 2 left divided by 2, multiply by 2 over 2, collect both terms in the numerator, and realize that 2 left plus right minus left is the same thing as left plus right divided by 2. Same math, but now it's not susceptible to overflow. Okay. Now, is that the thing I'm looking for? If the array on the middle index is equal to the key element, guess what? I'm done. Return the index at which you found it, middle. Else if the array, or the key is less than array of middle, then I need to search the left part. Else if the key is greater than that middle element, then I need to search the right part. No change here. If you break out of this loop, not having found what you're looking for, it means it doesn't exist. So return -1. Okay. How do I search the left part? I've got my left index and my right index, and my middle index right in the middle. So what do I update if I want to search this part? My right index. Right becomes m minus 1. I've gotten really good at mirroring all my fingers over the years. So if I do ever make a mistake, let me know. All right? Else if I need to search the right part over here. Right? So what do? I update my left index to m plus 1. I don't stay on m because I already looked at that. I just looked at that right here on line 35. Right? So I update my left index to be m plus 1. There we go. Yeah. Oh, thank you. Where? Oh, it should. Sorry, it should be middle. There we go. I was shorthanding that. Sorry. MLR is what I would usually do. I know what they stand for. I don't need to write it out. No, I do need to write it out if I'm illustrating it. Right. There we go. Let's test it. So not index of, but binary search on the same thing. Found element. Oops. Binary search. Right. And we're searching for 6. CSCE 155E. GCC demo. A dot out. Found element at -1. -1 was an unsuccessful search. Wait, it's right there. Why didn't you find it? Again, what does binary search rely on? It relies on it being sorted. It's exploiting that structure. Is this sorted? Nope. All right, so let me go ahead and cut and paste this. And you tell me how to sort this now. Manually. We're just whiteboarding this. Right? So what should go first? Hint. 2, why? How did you go about finding that element? You looked through the rest of it, and you found the minimum element, and then you put it in the front, removing it from there. Now do the next one. What comes next? 3. How did you do that? You looked through it and you found one of the minimums. Oh, there are 2 of them. So I'll just go ahead and take this one and put it in the front. What comes next? The other 3, right? Dot, dot, dot. What comes next? 4. Taking that out. How are you sorting this? This is amazing. You figured out how to sort things. All you're doing is you're going through all of them, selecting out the minimum and putting it at the front. Right? Note the emphasis on the word there, selecting. This is selection sort. Right? It's something that we'll look at after the break. Fast forward. 5, 6, 9, 9. They're already where they need to be. Is that the same? Looks like it to me. Let's go ahead and rerun this. Now that it's sorted, found element at index 5. Oh, cool. All right. Where is it? 0, 1, 2, 3, 4, 5. Right. I should also test for extremal elements. Can you find that too? It should be at index 0. Wonderful. Can you find that 9? It should be at index. Ooh. Which one does it return? Who cares? It found one of them. 0, 1, 2, 3, 4, 5, 6. Looks like it found that one. Well, I wanted it to find that one. Okay, why? What's the difference? Right? If there's a difference, you need to program that difference. Okay? What else do I need to test for? Wrong values, or values that are missing. 42. This should return a -1. I did not find what I was looking for. Oh, I found it at index -1. Perfect. All right. Now, how do you sort this without having to switch things around? So let me undo this and give you a preview in the next 5 minutes of what we're going to do next, or after the break. Right? I don't want to have to sort this. So what I'm going to do is I'm going to call a function called qsort. Q stands for quick. It's going to be quick about it. Right? And I'm going to sort the array. I'm going to sort n elements in the array. Each element takes 4 bytes because they're all integers. Is this the right order? And qsort. Is it? Come on. Base number. Yep, it's the correct order. Excellent memory. Awesome. Thank you, brain. And then what I need here is, how do you sort integers? I need something here. That something is called a comparator function. Int, cmp int, const void star a const void star b. Right? And what we're going to do is we're going to simulate that string comparison. We're going to return something negative, positive, or 0, depending on the relative ordering of these things. Right? So let me go ahead and show you really quick, and then when we come back after the break, to remind you of what it looks like. Const int star a, or x, is equal to const int star on a, x and y. What I'm doing here is I'm converting those generic void pointers, right, into integer pointers. And now I can look at what's stored in those memory locations. If what is stored in x, dereference, is less than what is stored in y, then I'll return something negative. Something. Why does it have to be something? Just -1 is fine. Else if whatever is stored in x is greater than what is stored in y, I will return something positive. I don't write plus, though. Right? Otherwise, if they're equal, guess what I return? Something 0 is 0. Right? That's the only thing that's 0. Let's run this now. Remember, it was unsorted. And now, through the magic of those two elements, of calling a basic sorting algorithm that's built into the language and telling it how to compare two things. There we go. Oh, well, that's not interesting. 2 would be interesting. Where is it going to be? At index 0. It's automatically sorted for me. Want me to prove it? For int I equals 0, I is less than n, I plus plus. Look at that array now. Printf. Array sub %d is equal to %d and the line. And that's going to be I and array of I. Come on. It's sorted. 2, 3, 3, 4, 5, 6, 9, 9. Right? I didn't have to go through and manually do it. I didn't have to write my own sorting algorithm, right? But we will, and we'll show you why you don't do it. Right? Instead, I wrote this function that took these two things and returned something negative, positive, or 0, depending on the relative ordering of them. Right? And then I handed that off to qsort, and it took care of the rest for me. Right? I did not make a function call. That's the function name. What do you think that is? I'm qsort. I don't know how to sort these things. Well, there's something over there that will help you do that. That thing over there. What am I doing? I'm pointing. I'm pointing not to an integer, not to an array, but I'm pointing to a function. These are called function pointers. And that's what we'll start with on Monday after Turkey Day. Have a good break.